Welcome everyone to our second webinar from the CoDEMO project, CoDEMO 5.0, which is about the co-creative decision makers for 5.0 organizations. Today we are very happy to welcome our partners from Lucian Blaga University in Sibiu. They will give the second webinar titled Examples of Educational Utilization from their node, from their OMiLAB node in Sibiu, which is part of the value co-creation laboratories developed during the project. Before I hand over to my colleagues to show you the experiments, I want just to give you some brief information how it's the webinar organized. It is recorded, so the recording will be available on our website at the end of the session. In case you have questions, we encourage you to ask us and challenge the presenters. You can either put your questions in the chat and I will do my best to manage it, and I'm sure we will have time at the end to go through them. Or you can also unmute yourself at the end of the presentation and ask directly. Please feel free to use the reactions in Zoom if you want to share something. We are very happy to have you with us in such a big number today. I think that's it from my side. Enjoy, and I give over to our colleagues from Sibiu.
Welcome to online, let's say, to Lucian Blaga University of Sibiu. My name is Adrian Floria. I'm a local leader of CoDEMO project from this university, and I'm happy to share with you, together with my part of the team, let's say a third of CoDEMO team from Sibiu, some examples that we developed in our university since beginning of 2020, where we installed the OMiLAB laboratory in our Faculty of Engineering. So just briefly, I will share you some details about laboratory. We are quite here in the OMiLAB node, and because there are some complex application, we just explain a little bit the concepts, and then we'll show some videos with recording of our application in progress. But as Julia said, we are open to discuss whenever is necessary now, or based on email or other messages to us to explain how we can do also with the source code, on actually to be, let's say, a flavor of developing some application in your university or in your OMiLAB node. So for this reason, actually, we prepare five prototype here in Sibiu that was developed around almost 3-4 years of activity, not just in a night, let's say, and with trial and error and helping each other, or just to increase the human resource or the human capital in our university. These applications are based usually on simulating using robots, because maybe some of you know Sibiu is an industrial city, and most of our partners are from industrial sector, and we have also some of my students that are here part of the webinar. Some of the presenters are part of the industrial companies, not only from ULBS side. So we will briefly detail how it works in a shop floor, an AGV, autonomous guided vehicle, who need to carry some heavy things and deliver to some collaborative robots. Then we will show some example of how we can park a car. We know all of us that smart parking is a challenge in our nowadays in smart city challenges. And we have two scenarios where we can park to a specific point, but also to leave the car autonomously decide where can find a free spot. Also, we develop some application where we have a mobile robot who go through a warehouse, could be an agricultural warehouse or an industrial warehouse, and scan some QR codes and introduce in a database, making, let's say, a collection of data about what we have in this warehouse. Also, we want to show some application based on deadlock situation when autonomous mobile robots could stop each other, and how to prioritize some of them. And also, the last application is, let's say, a little bit in the middle between industry environment and or working environment, having, let's say, the humans in the middle, and we want to see if the person stay in a good position of their desk, and also the air quality and other parameters are okay. Many other things or project that we developed until now, you can see on our OMiLAB node webpage. And let me present briefly my colleagues. I will start with my colleague Daniel Morariu, who most of the partners from CoDEMO know him. And also we work together with Aida Manta, which is a master student at Embedded Systems, with Melissa Stoishor, who is now also engineer in France on the Nice company, and Andrei Potreușanu, who is also my PhD student, and they all of them were my former student to bachelor or master diploma. So I invite now Aida to start explaining the rest of the application. And as I said, we are open to any question finally when we finish our presentation.
Thank you, Mr. Flora. Hello, everyone. As Mr. Flora said, we will present you 5 applications, but we will start with presenting the model behind the implementation. Some of you may already know it. This model has 3 layers: the design thinking layer, the conceptual modeling, and the cyber-physical system. Us at CBU, being a more implementation-focused university, all of us being engineers, or me being halfway there of an engineer, being in my master's studies, our main focus here in CBU was more on the cyber-physical system layer, more exactly the implementation of the project, as you will see later on. As Mr. Flora said, due to the short time, we will present to you the main ideas behind each project. We will not go into much detail about the coding behind each application, but we are open to any discussions whenever you think like you want to ask more questions. I will now move on to the first application, which is automation of an assembly line assisted by a robotic arm and a mobile robot. As Mr. Flora said, in CBU, we have a lot of industry, we have a lot of companies. Me and Andrei both work in automotive companies, so we have assembly lines somewhere in the factory. Now, many of nowadays companies implement such behavior using mobile robots and robotic arms. This is to help not only the factory to act more rapidly, but also to help the humans, because as we know, all of the goods that are transferred from one point to another in a factory are not always the easiest ones. They can be heavy, they can be, I don't know, tall or other big dimension. So it affects negatively the person that carries them. So many factories decided to implement this kind of robotics using mobile robots and a robotic arm, not only to facilitate this process to be more fast, but also to help the humans avoid certain negative impacts on their health. Now, how this works, each mobile robot can be loaded and unloaded, and it transfers the goods from one point to another, for example, from the storage area to the assembly line. And when it reaches its, let's say, destination point, whichever that may be, the robotic arm will come into place. It will take the goods from the robot, for example, and place them on the assembly line, where then the humans can intervene and, I don't know, do more delicate tasks on each component. We will now show you the layers that I have presented earlier. You will see that in this presentation, each project will be explained first the design thinking, then the conceptual modeling, and then in more detail, the cyber-physical system. We will show you the main idea behind the flows, and also a video to demonstrate how each application works. Now for this application, you can see here that we have thought of 4 main scenes behind this process. Firstly, the mobile robot will pick up the goods from the storage, for example. It will deliver them to the destination point where the robotic arm will be waiting. When the mobile robot has arrived to its destination, the robotic arm will unload the mobile robot, and then it will do further tasks, but the mobile robot being free, it will return to the reloading area, as I said earlier, to improve time management. In the conceptual modeling phase, you can see the scenes that I have explained on the previous slide. But this conceptual modeling being the middle layer, it's like the transition between the design thinking, which is more of an idea, more visually explained, to the cyber-physical system, which is pure implementation. This model is like the transition between them. We can also see the ideas from the design thinking, but they are explained in a more program-orientated way. So here you can see in more detail each scenes that I have presented earlier: the pickup, the delivery, the reload, and the storage. Now, as I said earlier, we are more focused on the implementation. You can see here a little part of the flow implemented in the app. You can see here that this is the flow for the robotic arm. It takes the goods from the mobile robot and it places them to the designated spot. In our video, you will see we have 2 designated spots, one on the left side and one on the right side of the robotic arm. And here is the flow behind the mobile robot. At the first glance, it can appear very complex, but if you break it down in small pieces, you can see here that most of the flow is just the implementation of the path that the mobile robot must take. As you can see here, just for a short example, we have the follow lines nodes, the turn left until in line, follow line. So basically, it just follows the predefined path that each mobile robot has for transportation. We will now show you how this application works. This project models an industrial agricultural warehouse and shows how 2 robots, a mobile robot and a dogbot, can collaborate in creating an automated loading and unloading station. The mobile robot is loaded manually and then it will go to the dogbot to be unloaded. We will now show you how this process works. The mobile robot has now arrived at the unloading station, and the dogbot will now unload 2 carts from the mobile robot. This unloading will be done in the container on the left. Now the mobile robot will go back to the loading station where it will be loaded again manually. robot has arrived at the unloading station for the second time, and now the robot will unload the cars in the container on the right. So this was the demonstration that we have proposed to show you. And as you can see here, we have programmed the robots for this specific assembly line, but it can be programmed for whichever other assembly line. Moving on to the next application, it is a part of parking of a mobile robot using modeling languages. We have thought of this application because it will impact in a good way our whole community, not only just the industrial area. As Mr. Flora said earlier, this parking system works in two ways. One of the applications requires an input from the user. The user will select a specific parking place in which he wishes the car to be parked in. And the second scenario is when the robot will try to find by itself a free parking space. Here in the design thinking area, you can see the scenario that we thought of. We have taken into consideration exactly the CBU area where people commute from one part of the city to another, or from a neighboring small village to the city. So the main scenes behind this application were getting the car, driving to the city, and the final step where we come in, parking of the car. You can see here a more detailed implementation of each scene. And here we go to the specific implementation for each one of the scenarios. The first scenario that we will show you is the parking in a fixed parking location. In this flow, as you can see in the image on the right, the code verifies which parking space was selected. In our case, we have 6 parking spaces, 3 on the left and 3 on the right. And the flow checks which one was selected, and the path to that parking space has been mapped in the memory, so it will take the necessary route to arrive at the destination. We will now show you how it works. This application models an automated parking system and shows how the mobile robot can park itself in the chosen parking spot. In this simulation, we have a parking lot with 6 parking spots. We will choose parking spot 3 to show you how this system works. This first stop is for parking spots 1 and 6, the second one for 2 and 5, and the third one is for parking spots 3 and 4, and now the mobile robot will go to parking spot 3. And this was the model of an automated parking system. So this was the first scenario of the parking application. We will now present to you the second scenario. As you can see in the flow on the right, it's a little bit more complex than the first one, but that is because this scenario works with real-time data. We have an external component, which is a proximity sensor, which detects if in a parking space it exists an obstacle or not, that obstacle being an already parked car. We will now present this little video to show you how it works. We will now show you the same automated parking system, but now another version of it. This time the mobile robot will park itself in the first 3 parking spots that it finds. We will now show you how this works. The mobile robot will start its search with parking spots 1, 2, and 3, and if all those are occupied, it will go and try 6, 5, and 4. As you can now see, every time it finds an occupied parking spot, it reverses and tries the next one on the list. because it found 1, 2, and 3 occupied, it will go back and try 6, 5, and 4. And now, because it found parking spot 6 empty, it will park itself there. What I have not mentioned earlier, which I will mention now before moving on to the next application, is that we have thought of this simulation due to the fact that CoDEMO is a project oriented on sustainability and creating a more eco-friendly environment. So we have implemented this simulation in order to, first of all, as it's called, to simulate this scenario and to find ways to improve it in order to decrease fuel consumption, and as a result, the air pollution present in big cities where the traffic is heavier than in rural areas. The third application we will present you is modeling a simulation of an automated system in an agricultural warehouse. Even though this application was initially designed with an agricultural warehouse in mind, it can be applied to any kind of warehouse, no matter the field it's part of. So how this application works, this uses also an external component, which is an attached camera to the mobile robot. The mobile robot has a predefined path that it goes through in the warehouse and reads all the QR codes it finds on the way. The more complex part of this application is not the programming of the mobile robot, because the route is predefined. And as we have seen in earlier images in this presentation, even though there are a lot of nodes that are required to implement such a predefined path, it is not as complex as the other part of this application, which is the image processing. As I have said, we have an attached camera to the mobile robot, and that camera will take a picture of each QR code and send it forward to be interpreted. This application is also a very good example of how multiple technologies can be combined to create more complex and more efficient projects. In this case, Firebase was used for the database, Python was used as scripting for the image processing, and for the implementation of this part, the Visual Studio environment was used. And also the communication is done through requests of type HTTP. Being, as I said earlier, the mobile robot part of this application is a little more simpler than the rest of the other projects that we have presented, and that is why here we have only one picture. But as you can see here, the mobile robot has the path designed, and it will read all the 6 QR codes that are present. As well as the conceptual modeling, it is pretty straightforward. We check if there are any QR codes to be scanned, and if it has arrived at the final destination of the route. Here you can see the implementation of the mobile robot, and now we will show you how this works. As I have mentioned before, this application was firstly designed with an agricultural warehouse in mind. So each of the data represents information about the goods on the shelves, which are either fruits or vegetables. Here, even though it's written in Romanian, I will tell you what there is in the database. We have the type of fruit or vegetables. For example, on the first line, we have golden apples or kiwi, or on the third line, we have strawberries. We have then the quantity, the price, the country of origin, the date the QR code has been scanned, and the time it was scanned. And after obtaining each information from the QR codes, the data will be sent and saved in the database to be further processed later. Now, the fourth application we have proposed to show you is dealing with deadlock situation of autonomous mobile robots. Now, if you may have heard about such situations, because such mobile robots are not used only in factories, as we have presented before, but also in the concepts of smart city for transportation of people from one point to another. Now, the greatest advantage of these robots is that by eliminating the human factor, let's say, we also eliminate being tired or stressed or losing your attention to the road, and as a result, these kind of transportation modes are way safer. But in this safety-oriented way, the robots are programmed to stop whenever they encounter an obstacle, but such an obstacle can also be another mobile robot. Now, in this situation, we will find a deadlock because each robot, when it faces each other, it will block, it will stop, but none of them are programmed to know how to prioritize the other, which one of those two to let go first. So that is why in this situation, we have thought of a way of prioritizing. This way is applied. This project was done with a warehouse in mind, as we will show you. So you can see here the scenario that we thought of is one of the robots was loaded, one has been unloaded, and in the middle of the road, they meet again, and here they would stop and would not go further until an external factor intervenes, which is us humans. So we have thought of the way to check which of the robots is loaded and which was just unloaded, and to prioritize the robot that is loaded over the one that is unloaded, as you can see here in these images from the design thinking. Here you can also see the main steps behind the implementation of this scenario. And here you can see how the commands are further transferred to the mobile robot. We have the function call from the app, as we have seen in the flows before. All the function codes are transferred to the Raspberry Pi, and the Raspberry Pi is the one that communicates with the server and transfers the commands to be executed. We will now show you how this works. As you can see here, the unloaded robot will let the loaded one pass, and then it will continue its route. Now, the reason that we thought to implement this application is because such situations have also been encountered in the factories that we work in. For example, one of my colleagues actually had as a bachelor project, as a bachelor thesis, the idea was to implement a project to identify which are the most common causes that such a mobile robot stops, because there were a lot, and it basically stopped the process of lowering time consumption. It actually worsened it because the robots had to wait until the path was cleared, which meant waiting for a human to clear that path. And from that analysis, we have obtained as a result that most of the time when two robots meet, that's the most common cause of them blocking in the factory. Now we will present to you the last application. As Mr. Florea said, this one has a different focus than the ones we have presented. We have implemented this application not only for use in the industry for our colleagues in open offices, but also as maybe a personal use. The idea behind this project is that we tend to pay more attention to how the outside environment affects us, the pollution, the temperature, etc. But we kind of lose that focus when we are in an inside environment, especially in an office. And after a little bit of research, we have found out that such deviations from standards, because there are standards, we have the optimal temperature, humidity, light, air quality in an office. And if these parameters are not in the approved ranges, it can affect negatively each person. As you can see here, they can create dizziness, headaches, muscle memories if the position is not correct. And these problems can be short-term, they can pass in a few hours, but if they're repeated consistently, they can lead to long-term health problems. And that is where the system would come in. The system would come as an informational way of helping the user, because we will take information and we will analyze it and show it to higher management or maybe the user himself or herself, and necessary actions can be taken further. For these applications, we have two scenarios. The scenario where the person is not at the desk, in which case we will not analyze the ergonomics nor the ambiental environment, because we have considered that there is no advantage to that. But if we detect a person at the desk, that's when we analyze all of the factors that I have just mentioned. Now, what I have not mentioned is that the system is consists of two microcontrollers, one of them having an integrated camera and an integrated Wi-Fi module, and a few sensors. Now, this is the scenario when the desk is empty, when the people are not working. So after taking the picture and analyzing it, we can tell if the person is working. If not, we will try again in a few minutes. Now, if the person is working, that's when we also get the data from the sensors, we analyze all of the information, and we save it into the database to be later shown to the user. This application was implemented mostly in Node-RED, and as the applications in BIAP, they are a flow-based method of programming. As you can see here, we have requests sent to the microcontrollers, and that is how we get the data, because we made the system to be completely detached from the computer. Here is the part where we interpret the data and write it into the database. And which I have forgot is to show you the demonstration of how this works.
Ambiental environment in which an employee is working and his or her position at the desk. You can see the setup here. I'm working on my laptop, and on the left you can see the system. I'll now show you how it works. I will trigger it manually. It will send a request to the microcontroller. It will take my picture. And after it has detected that I am present at the desk, after 30 seconds, it will send a new request to the system to also receive the data from the sensors about the ambiental environment. After analyzing it, it will write the data into the database. The user can see here the results. I will refresh it. This report is connected directly to the database. And now we can see the last entry. It has analyzed the temperature, humidity, and light, and my posture. My posture was optimal. And here in this graphic report, a user can see the deviation from the standard. The green circle is the optimum values, and you can see how the other values have deviated.
So as I have just shown you and mentioned before, it analyzes the ergonomics and some factors of the ambiental environment, the temperature, the light intensity, and the humidity. Regarding the ergonomics, it analyzes what is visible from above the desk, the upper part of the body, and also the presentation that the visual report that you have just seen in the video is done in Power BI, because this technology allows not only a very visual and interactive way of presenting data, it can also be connected directly to the database, so the user can have access anytime to the latest data. So these were the projects that we have proposed to show you. I hope you have enjoyed, and I will let Mr. Florea continue with conclusion, limitations, and future development.
Okay, thank you, Aida. As I said, there are, I think, even in a brief or in a speed up presentation, there are a lot of work behind. But we show, I hope, for everybody that the tools or technologies provided by OMiLAB, but also others, could be combined and help to simulate some real case scenario that happens in industry, agriculture, or in our daily work. Of course, there are also some small, let's say, limitation, because you can see in the movies that sometimes the mobile robots should be adjusted a little bit to go to the line, or we need a lot more power, but also we have problems when we want to synchronize the both bots and work together to prioritize. Of course, in the ergonomics application, this depends also of the position of camera or of the person. But as I said, there are no application without short constraints, let's say. And our intention is to apply such of application based on requirement or requested from companies or from agriculture farms to apply IoT, to apply AI or other technology, and hopefully show their feasibility in the laboratory, and then can start bigger project working to this partner, let's say. So in embedded system with or augmented reality, and can help to solve many things. So we can also provide, let's say, the source code from our application, and we are happy to hear your comments or your suggestion, because let's say it's an ongoing work that we intend to do in our department and our university. So I will stop sharing the screen, and I'm ready for your questions.
Thank you very much. Thank you for showing us these experiments. I think the team deserves a round of applause. It was very interesting what you showed us, all the different experiments, what you can do in the lab. Now I open the floor to all the participants in the webinar. I see there is already a question from Thomas. Should I read it from the chat, or you would like to ask directly?
Hi, yeah, I can also do it again. And yeah, we were interested in these scenarios, very interesting. How long does it take on average to develop these kind of example scenarios? It's important for us because we want to develop this, for example, with students to get a feeling about it. Because, you know, we are quite new in this OMiLAB space and world, so that's going to be interesting.
Yes, thank you, Thomas. What I want to say that besides the work of our students, I think will help also the NEMO Summer School, because two of the applications that we developed were based on two bachelor students that I had and that participate in 2019 in the NEMO Summer School. This year also Andrei will follow this classes, let's say, and to become a digital engineer as we want to be. So this is first step that could help, but I want to say that from the computer science point of view, when they heard for the first time about modeling, were very disappointed. They wanted to run, to don't work. And then we turned back and we discussed and put it all together. And I think that we show nice and interesting things. Usually, each application could be around 6 months or maybe more, because also the students or the students from CBU are good students, come to study, but also work in the companies, and the time, let's say, dedicated for such project is not very much. So could be less than 6 months, but usually, because you need first to understand the whole thing, to understand the design thinking layer, the modeling, but also how to work with microcontrollers to be in the same network, to can communicate each other, to learn about HTTP requests and other things. Before to have also a project that want to apply or develop, so the design thinking part. But of course, this take for us around 6 months till 9 months for each project.
Xavier speaking. Perhaps a point we can underline is that there is a lot of reusable material and perhaps opportunities of collaborating when you need to build a scenario, because it is, as you understood, built on small pieces of code and functionalities for each robot. And so these small pieces, you can reuse it in case you have exactly the same programming language, or I don't know. So this is also an opportunity of collaboration, at least.
Yes, exactly. So just to add here, as you notice, all of the experiments showcased, they start from the top layer, from the design thinking, and then from the concept of it, and then you decompose it until you reach the cyber-physical elements. I put now in the chat again the link that's directly from the OMiLAB node in CBU, where you have again the contact information. And then all of these experiments will be soon available on a platform that we work on as part of the project, where the showcase will be highlighted. I see another question in chat from Serge. Would it help to first run a pure computer-based simulation, then transfer it to the physical world? Would you like to? Serge, maybe if you would like to explain the question.
Exactly. You are on mute.
Oh, we don't hear you.
No.
Okay, but maybe let's start with the question in the chat first.
Yeah, actually, as I said before, we started from a real situation. We try to adapt to a real problem from industry first to let's say, teach our student how to program such a small robots for a specific task. Of course, as Aida said before, in the real shop floor could appear not only other AGV that block you, but also could be some boxes or other things. And the AGV should decide, let's say, in real time, what path to follow or to surround, and when to stop or other things. So this is only a small piece of our work, but we first want to see that could be applied later or developed further in the real situation in companies. I don't know if I explained quite well, but
yeah, I think this is also one of the advantages of modeling, right? Because then you are more agile, more flexible in developing the scenario, and also in a simulation, in a pure simulation setting. Sometimes you don't observe everything. If you notice in the videos, sometimes it was needed to for the M-bots to help them a bit, steer them, and this is something that you don't notice in an only simulation setting. This was needed because after a few runs, the battery is lower, it decreases. So then when it's 100% the battery, then the M-bot turns 90 degrees. But when the battery is only at 80%, then this turn is not 90 degrees, is then maybe 80 degrees. And then you have to adjust a bit. So all of this you can only, it's the modeling that helps you, then you can be agile and change some things in the model and then adjust the parameters. Thank you, Serge. If you still want to add something additionally. Oh, all good. Thank you. Are there further questions?
of course, the laboratory could be visited by all that will come in October at CBU Innovation Days, and also with other occasions. So we are happy to show such application and try to work with Marquardt company that is our partner in CoDEMO project, and also together with OMiLAB on such case studies that will be applied in the shop floor, let's say, a little bit further.
Yes, thank you. So next time when you are in Sibiu, please contact Professor Floria and his team to see these all the experiments in the lab. And of course, join the Sibiu Innovation event.
So perhaps one last question on my side is, these scenarios, were they developed with the orientation only to teach students how to program such applications, or do you consider that there is also an interesting point to demonstrate a solution for real industrials?
Yeah, thank you, Xavier, for the question, because it's very important. What I observe in my, let's say, 20 years of teaching, the students from computer science want just to develop, to write programs, and not necessary to see the whole project, the holistic approach of the. So it is very important for us to explain that such scenario, such real case scenario will appear in many things. But of course, some of them are making internship and they learn there that such scenario exists, but don't know how to tackle the problem. So it's better to see from the both sides, not just implementing and you don't know what you implement and the problem that you will solve.
Thank you. We can see Julia, somebody else, Yolanda.
Yes, I think Yolanda, do you have a question?
Hi.
Hi.
Hi, thank you all so much. Thanks, Adrian, for the session, and I completely agree with you. This is Yolanda here from South Africa, and I also attended the OMiLAB NEMO School in 2019. So I have a process engineering background, so industrial engineering, so I agree with what you're saying. In terms of, understanding the holistic view, like the actual process, before actually coding it in or developing. So the question that I have, I'd like to do a bit of a practice, like with a few scenarios. So is it possible that we can get some of the scenarios sent to us so that we can practice? Would that be something practical? Just to sort of get my mind in the mode of things again. Yeah, I think for me, that's the request that I have. Thank you.
From my side, I think the science should be open for everybody, and the engineering part should be validated by everybody. So we are happy to share or to explain in some, let's say, documents or even the source code what we did, and also to have feedback and do better or to apply to other tasks. And yes, we can do just write an email and we will see how can collaborate. And of course, the things that are, let's say, validated by OMiLAB, who is let's say, the provider of tools or the software part. But the source code that we developed is free to use by everybody.
Yeah, the tools as well, everything is open source. So I'm sure you can have the setting. Yeah.
Absolutely. Thank you, everyone.
Thank you so much. If there are no other questions, I would like to propose a group picture, a virtual group picture from this webinar. So if you would like to be part, maybe open your camera. And then I'll do screenshot. I'll just give it a few more seconds because I see cameras appearing. Great, thank you. So at 3, we all smile, right? 1, 2, 3. Great, thank you. Thank you very much for being part of this webinar and joining us today. And please stay in touch with the project to follow our updates when the next webinar will take place. You can find us on LinkedIn or also on the homepage. If you have further questions, don't hesitate to contact us and contact also the team from CBU. Thank you again for being here. Thank you to Adrian and his team for the presentation. And the recording will be available on the homepage at the end of the day, so you can all the time go and check again the experience. Thank you. Have a nice afternoon and see you next time. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye.
Thank you, Julia. Bye-bye. Thank you, Adrian.
Bye. Bye.